Okay, welcome, Jordan and Victor and Jacob and Jesus and Ralph, and hopefully we'll get a couple more coming. Let me share my screen and talk about what we're doing today. All right, so the plan today is I'll start out, as always, with any questions you might have, and I'll do what I can to answer. And then what we're going to do, last time we did arithmetic, and we defined how do you do arithmetic, at least some arithmetic. So for example, we looked at, I'll answer the question in a bit, but I want to go through the agenda and then I'll answer questions. Sound good, Ralph? And then we looked at, so we looked at addition, subtraction, scalar multiplication, and multiplication. So now what we're going to do is we're going to look at properties. So what can you say? You think about all the properties that you have of regular numbers, and do they follow for matrices? And the answer is some do and some don't. So we'll talk about that. Then we're going to get into what's the fourth big arithmetic besides addition, subtraction, and multiplication? You better all know this.
Division.
Division?
Yeah. You don't know it, you don't belong in this class. Division. Yeah. So it'd be nice, since that's kind of important, division, at least with numbers, to be able to divide. And so we're going to realize, just like numbers, can you always divide with numbers?
No.
No, why
you can't
can't
divide
you?
by 0.
Right. We're going to find out that you can't always divide with matrices either, but it's much, much more complicated. So we'll get into that. So we'll start out with talking about the identity. That's kind of like 1. And then we'll get into the inverse. So we're going to get the multiplicative identity, which is like 1, except it's going to be I. And then we'll get into the inverse. Okay. And does an inverse exist? Does an inverse not exist? It really depends on the matrix. So we'll get into that. Then we'll get into symmetric and skew symmetric matrices. That's actually quite easy. That has to do with transpose, and that's no big deal. So then we'll get into how do you find the inverse of a matrix. So I want to mention something that I mentioned, I think I mentioned it shortly last time, but you may not realize, but a matrix is a function. Maybe I don't think I did mention that last time, but a matrix is a function. They're very different than numbers. It's actually a function, just like a Jacobian is. And that's why we talk about inverse and not reciprocal. Because with functions, it's not the reciprocal of a function, it's the inverse of a function that you want to be able to have to be able to think about what we need to think about. So similarly for a matrix, which is a very special kind of function with a weird domain and range, but it is a function, how do you find that function's inverse? And then we'll talk about properties of an inverse matrix. So what do you have? What things can you do? So for example, if we have two matrices A times B, and we want to find the inverse of A times B, is it the inverse of A times the inverse of B? What do you think? Any guesses?
I'm going to say it's probably not that easy.
It's not that easy, but it's actually not much harder, and we'll get into it. There's a formula, and it's a really easy. It is actually just about that easy, but it's slightly different. And if you do what you want to do, which is A inverse times B inverse, it's wrong. So we'll talk about what you have to do, and we'll have some other properties of inverses also. Okay, so that is the plan, and I want to mention one more thing. What are we talking about a week from today?
An exam?
Nope. It's a trick question. That's a hint. I'll hear it. The answer is nothing. You guys know why nothing?
Oh, it's a holiday.
It's a holiday. So I want to mention, I always like to let you know when a holiday's coming. So a week from today is Martin Luther King's birthday. And even though we're online, that doesn't mean we shouldn't have holidays. Don't you agree? So yeah, Monday's totally a holiday. There won't be any, no webinar, no office hours. I might still answer email, but only if, I have nothing else to do, because COVID time, usually I go out and do some fun stuff for the weekend, but now there's like travel bans and stuff. So probably isn't going to happen. So I will look at email, or probably, but otherwise we don't have class on Monday. So that's a complete day off. Sound good?
I have a quick question for you, Larry.
Uh-huh.
I don't know if this will happen in the, at least not this week, but is there still a protocol on snow days if it's like dumping snow outside?
Just that I'll be looking outside and smiling, because that means I can go skiing afterwards, unlike today where it's not enough snow.
Yeah.
Snow doesn't stop you from going from your bedroom to your living room, does it?
Yeah, I was just curious.
Yeah, no. At least from my bedroom to my living room, if there's 30 feet of snow, I can still get there. So the reason why we have snow days is you can't go from your bedroom to the college when there's 5 feet of snow on the ground. That just
Got
happened.
it.
You see that?
Yeah.
Yeah. The only thing that could happen, and let's cross our fingers that it doesn't, is we could have a power outage or an internet outage.
Mhm.
And that's going to be one of those unannounced outage days, because we won't know until it doesn't work, right?
Mm-hmm.
And that could go on either it could go on at my house, or it could go at your house. And that we won't know until it happens. Does that make sense? So this is, snow days don't happen. Power outage days could, but snow days don't happen. Yeah. So it's kind of like the very first time I ever taught calculus, snow days didn't happen either. And remember, I'm old, so it was not because it was online, because the word online didn't exist. And know why?
You weren't in Tahoe.
Yeah, even more. I was in San Diego.
Yeah.
If anyone wants to go to UC San Diego, do not think that there's ever going to be a snow day, because there will never be a snow day at UC San Diego. Just let you know that. So this is kind of like pretend we're in San Diego. Sound good? So yeah, no snow days. Let me answer Ralph's question. During the exams, would you be in a Zoom meeting during the time to ask you for questions? My plan was not to do Zoom, more email. But the idea is, it's an exam. I mean, there shouldn't be a lot of questions, because I give you the question and you do it. And I'll try not to make them too confusing, but they're hard, doesn't mean not hard, but the wording should be like the rest of the wording we've done. So I'm not going to do Zoom, but I'll be on email, probably most of it, maybe all of it. So that's what I'll probably do. I think email is more appropriate for that. Any other questions?
Does that include homework questions, or are we going to get into that later?
Yeah, that includes homework questions. We're in Q&A time. This is Q&A.
All right. For 2.1, could we go over 5 and 7? I'm a little bit confused as to what the questions were really asking.
Okay,
because they
find it.
They were dependent on some parts of the book, like propositions or something that I couldn't find out. So
okay, just a minute. 2.1, what number? 5 and 6?
5 and 7.
5 and 7. Let me find them. Just a minute. Oh, good. The reason I'm saying good is there's not a lot of formatting issues. So hopefully it'll let me do it. Just a second. Okay. So I was happy because copying and pasted works, because there wasn't a lot of math stuff. All right. So here's number 5. Sound good? So using only the properties given in Proposition 2.7 and Proposition 2.10 show that negative A is unique. Okay. Do you know what unique means?
Let me look back at my notes.
You know what the word unique means? It's an
Oh,
English
it
word.
means, like it's not replicatable, kind of.
Yeah, let me tell you what unique means in terms of a useful word, a useful idea of unique when you're trying to show something's unique. What it means is that if you have two things then they're equal. Does that make sense?
Okay. Yeah.
So if I have a B, if I have a B and a C that are both negative A, then B equals C. Does that make sense?
Yes.
Okay. Now we need to go to proposition 2.7 and 2.10. See if I can find those two. One of the things I don't like about the textbook is that sometimes it's hard to find things, right? You have to scroll a lot.
Yeah, that was my biggest problem with it, is that I couldn't really find something that was labeled Proposition 2.7 or Proposition 2.10 in the text, so I was a little bit confused.
Yeah, it's possible that they didn't number it right, but it's going to be the propositions about the inverse. So just a minute, I'll get there. Ah, I know you can't see that I'm having issues. Ah, what just happened? It's so hard with Zoom and other things open at the same time. Let's do it that way. No, it didn't work. Here we go. It kept zooming. Just a minute. So sorry, I'll take a second to find it, and then I can maybe copy and paste it in. Just a minute, it's in there somewhere. Permutation, multiplication. This section goes on and on and on. But it might take a moment. That was too late. I thought about clicking. I should have clicked it. Maybe I'll do that now. That wasn't it. Just a minute. Sorry if it's taken a while. Navigating with Zoom also on the computer, it makes it so much harder. I apologize, but it will happen. That one. No, that didn't work. Sorry. There is no clicking proposition 2.7. So now I have to go find it. I tried that. That was not good. So let's do it this way.
No, wait, Larry, click on the 2.7 or the 2.1 specifically.
You have to do that in the index, which I'm doing now. But
Okay.
But I tried to do it in the question itself.
Okay.
And that didn't work. So 2.7, no, 2. There it is. Okay, so we're looking for the negative. All right, so there exists a matrix A, a negative A, such that A plus negative A equals 0. So pretty much that's what we're using, and we can use the properties, and that's all we can do. So what we can say is the following. Now let's go back. Actually, you're seeing my word, which is not what I'm looking at. Just a minute. Okay. Sorry that took a long time. Okay, so what we have is that A plus B equals 0. And A plus C equals 0. Okay, and the 0 are the matrices, not the number 0. What do we want to show? So I'll even write, let's make it look like a proof, let. Then our goal is what?
To show that negative A is unique.
See, negative A is B, and negative A is also C.
To show that B equals C.
Yeah, that's our goal. B equals C. So our goal is to show B equals C. You following that? Okay. Now, what does it mean for two matrices to be equal?
That all their entries are equal and
Yep.
are in the, yeah.
So that means I can look at the ijth component and show they're equal. Does that make sense? So if A plus B equals 0, that means, so let me go to, that means that A sub ij plus B sub ij equals 0 for all I and j. Do you agree? Because 0 is the 0 matrix, it means the ijth component, and in fact, I'll even put that sub ij. But 0 sub ij is 0. So notice the first 0 here is the 0 matrix. The second 0 here is the 0 number. So it's a little confusing. And then we can also say that aij plus cij is equal to 0. Are you following that? Except that, there we go. Well, if aij plus bij equals 0, then aij equals negative bij. And if aij plus cij equals 0, then that means aij equals negative cij. Any questions on that? Okay, but aij is a number, not a matrix. Is that clear? So now I can use the properties of numbers. If I have a number equals a number, and that number equals a different number, then guess what? Those two numbers must be the same, right? So by transitivity, in fact, I'll even write that by transitivity of numbers, that tells us that bij, negative bij equals negative cij. But now these are numbers. And if I have negative a number equals negative a different number, what can I do to both sides?
Divided out the negative.
Yeah. Or I'm going to make it easier. I'm going to multiply by negative 1. And what I get that is that aij must then be equal to cij. Okay, but if aij equals cij, I'm sorry, not, sorry about that. This should be a B, not an A. Bij equals cij. But then if bij equals cij, by definition, that means B equals C. Have I lost you there? sometimes one of the most challenging things about this class is that you have to prove something that's really easy, but deciding what to write is really hard. I mean, it's really clear that this must be true, but how do you say it? And that's the hard part. You're only allowed to use properties of numbers and the definition, basically. And that's what they're trying to say in this. Is that clear or is that confusing? Okay. So hopefully that does it for you. Do you think you could do the other one now that I showed you this one? I didn't even look at the other one, but I'm probably not that different.
No, now that I know how to find those propositions, it should be a lot easier.
Okay, good. Okay, other questions before we move on? Okay, so let's move on. What I want to talk about is properties of matrices. And as I mentioned, there are a lot of properties of numbers, x plus y equals y plus x, that's a property, right? Hopefully you know the names of some of these properties. Like what's the name of that one? X plus y equals y plus x?
Transitive property.
Guess, another guess?
Associative property.
No, another guess?
Commutative.
Yeah, that's commutative. Yeah, that one's commutative. So there's all these properties like commutative. The ones you said, those are different properties, but those are important. We want to think about it too. Transitivity, associativity, distributive. There are lots of properties of numbers. And we want to say, well, do those properties work for matrices? Which ones work and which ones don't work? Does that make sense? Because, and the warning is some work and some don't work. So we got to be very careful. So let me give you these are properties, and maybe I'll make them a little bigger. I think that can rise that. I think that'll be easier to read. What do you guys think? And I have no idea that it wants to put space after number 10 because it's 2 digits, but couldn't get that space out. So let me just look at some of these and I'll even talk about the names of them. We just talked about this. So now, remember in this class, if I write a capital letter, what does that represent?
Matrix.
That's a matrix. So I'm not going to write down let A and B be matrices. I'm just going to assume that if I write it down in this class, it's a matrix. Got it? If I write a lowercase letter, what is that?
A variable?
Not necessarily a variable, because a matrix could be a variable too, by the way. You could have a variable represents a matrix.
Just a number.
Yeah, good, a number. And what we call it, you could say number, we usually call it scalar. But number's good. I'm good with number. Okay, so I just want to mention that like little k, lowercase k, that's a scalar. All right, so a plus b equals b plus a. That's the one I just said. That's commutativity. A plus in parentheses b plus c equals a plus b in parentheses plus c. What do you call that one?
That's commutative.
Commutativity is number 1.
Oh, yeah.
Number 2 is, I don't know. Yeah, associativity or associative. So this says, so these are properties, which means they're true. So for addition, commutativity, associativity, what do you call k times a plus b equals k plus kb?
Distributive.
Yep, that's distributive property also is true. A plus 0 equals a. Do you remember what you call that one? Identity, but in particular, you want to say it's additive identity because it's different than the multiplicative identity. Okay, this one you usually don't see written as a property, but I want to put it here because it's important. A plus a is 2a. Okay, I know that seems obvious, but remember that 2 is a scalar. So we're not even multiplying matrices here, but this does work. A plus a equals 2a. Okay, and in fact, if I wrote a plus a plus a, that would be 3a, as you might guess. Okay. A times 0 equals 0, and 0 times A equals 0, where A is a 0 matrix. I'm sorry, 0 is a 0 matrix. And maybe I'll even write, or 0 is a scalar. It works for both. And they're totally different, but you still get the 0 matrix out of it. So when I say 0, first 2. Or first one, actually, of each. So in other words, A times the 0 scalar is equal to the 0 matrix, and the 0 scalar times A is the 0 matrix. But you can also say A times the 0 matrix is equal to the 0 matrix, and the 0 matrix times A is the 0 matrix. So 0 is confusing. You're probably not used to 0 being a confusing symbol, but it is because 0 has lots of meanings now in this class. Okay. Now let's do one more multiplication. A times B times C, where A and B are multiplied first and then times C, is the same as A times B times C. Yeah, that's the associativity for multiplication. Okay, not scalar multiplication, actually, matrix multiplication. Okay, that should be an A, not an O. There we go. Okay. I think I already wrote this one. I don't need to write this one again. Let me get rid of that one. Okay, A times B plus C equals A times B plus A times C. Okay, that's the distributive property, but now it's matrix multiplication instead of scalar multiplication. So notice 3 and 8 are very different, even though they look similar. Okay, and A plus B times C is AC plus BC. What's missing here that you see in numbers? There's a couple really important properties that you see in numbers, but I didn't write here. Can you tell me? And it's really important to know this.
Something to do with the inverse?
Inverse isn't, I mean, you can't have inverse with numbers, but we'll get to inverses later, but just for arithmetic, there's just arithmetic. There's one that's missing that you see in it with numbers. It's definitely there. It's a biggie. I don't see you all jumping in. Okay, what about A?
Huh? Equals BA?
Yeah, AB equals BA. Do you know why it's missing?
Because it's dot
Because
product.
it's not true. It's
It's not true.
Yeah.
Not because it's a dot product. It's just not true.
I mean, there was homework questions where we had to like prove it was true in this one case with two matrices. You know?
Right, right. But in general, it's a false statement. Okay, and that's really important to know that A times B and B times A are not the same. In fact, there's a whole theory of it in quantum physics, by the way. I know someone might be interested, that there's a study of A times B minus B times A. And you could just trust me that that's like lecture after lecture after lecture of just understanding that. Okay, and there's words for it in the whole bit in quantum physics because it's a big deal. Okay, and you get all kinds of cool stuff. So let you know that A times B and B times A are not necessarily equal. Okay. Now A times 0 and 0 times A, those are equal. Those commute. Do you see that? So 0 always commutes, but not every type of matrix. Okay, A, B, and BA. In fact, you don't even always get the same dimensions. A times B and B times A. All right, what I thought I'd do, I don't have time to prove all 9 of them. Do you agree? But I'll let you choose. Whoever asks first, I'll prove that one. 1 through 9. Pick your favorite. Type a number.
How about, yeah, let's go with 9.
Okay, number 9. Okay, we want to show A plus B times C equals AC plus BC. All right, so there's a few ways of thinking about it. I think I'm not going to do, there's the book's way, but you could read the book and see that. I think I'm going to do it a different way, which is similar. So we want to prove, let me just copy and paste this so I don't have to lose it. Let's prove this one. Okay. So remember, how did I define multiplication? With a 3-letter word.
Row.
Well, row is part of it, but the main thing to multiply. Do you remember? I tell you, dot. Remember, it was a dot product. So if you want to look at, if you have an A times B, and you want to find out what the ijth entry of A times B is, you take the dot product of the ith row of A with the jth column of B, and that gives you A times B ij. Do you remember that? So the good news is we can do this, and I'm going to make an assumption, maybe you can tell me if I'm wrong about this, is that Bruce went over dot products and did dot products with you guys, right?
Yes.
Last quarter, since all of you said you took the vector calculus class. So I'm going to assume that you know the dot product stuff. So we know the properties of dot products. And the good news is it follows right from that. So let's take a look. A plus B. Let me go to there. And by the way, hopefully you're used to this. If you want to prove an equality, start on the left and try to get to the right. So what is A plus B by definition? Well, first thing, I don't really care about the whole matrix. I don't need the whole matrix. I need the ijth component in general. So I'm going to go A plus B times C. Ij. And I need to show that's A times Cij plus B times Cij. Does that plus B? Does that make sense? If I can show that, I'm done for all I and j. But the good news is that we have a definition. So what the definition is you take the ith row of A plus B and you dot it with the jth column of C. And just for notation, I'm going to do it by saying it instead of writing it because it just takes a long time to write it. So you would write this if you had to do a full proof. But I'm going to do the notation. And that is going to be, well, that's A plus B. I, where A plus BI is the ith row of A plus B. Dotted, I think I have a dot ability in here. There it is, dotted with Cj, the jth column of C. Any questions on that? Okay, well, what's the definition of A plus B? You just add them, right? Addition is really easy. Unlike multiplication is a little messier, but addition is easy. So that is equal to AI plus BI dotted with CJ. Anyone lost so far? Where AI is the ith row of A and BI is the ith row of B. But now we have this beautiful rule that Bruce went over about dot products. And what is that? What can you do with a sum of two vectors dotted with a third vector? Starts with a D.
Distribute.
Yeah, we could distribute because that's a rule that you've already proven in Bruce's class. So that's going to be AI. And then dotted with CJ. And then plus. And then we're going to have BI dotted with CJ. That's the distributive property for dot products. Okay, why am I done?
You just did it.
Yeah, because you look at the right-hand side, AI dot CJ is the ijth component of AC. So I guess maybe I should write that down. So that's equal to, let's see if this works. AC, nope, didn't work. Got to insert equation. So that's AC sub ij, by definition of what it means to say AC sub ij, plus BC sub ij. A lot of notation. There's not a lot of math here. There's a lot of notation. Do you agree? And the hard part, I think, is following the notation. That it in this thing, and I've just done it because I'm saying it. I'd write it out if I had the time. I'd say that, you know, if it has a single subscript with I, that means the ith row, and if it has a single subscript with J, that means the jth column. If it has a double subscript, that means the ijth entry. So that's what this notation all means. And I'm done. Because I've shown the ijth entry of the left is equal to the ijth entry of the right for every I and J, and that means they're equal. Any questions at all on this proof? Any questions? As I mentioned, I don't have time to prove all 9 of them because that took a long time just for one of them. So I decided to let you guys tell me which one you wanted. Some are easier than others. This was one of the longer ones, but it's not that hard, is it? Okay, it's a lot easier just a morning. It's a whole lot easier to watch than it is to do by yourself. Do you agree? A lot like kickboxing. All right, any questions at all on this? All right, now a definition, a very important definition. We'll be using this all the time. And that is the n by n identity matrix. And we always use the letter I, the capital letter I, to represent the identity matrix. Is defined by capital I sub ij equals 0 for I not equal to 0, and capital I equals 1. So that's the definition, and we're going to be using it all the time. It's an easy definition, but it's so important. I want to, just keep saying it because you've got to know this, because this is the one for multiplication, and knowing the number 1 is pretty important, isn't it? So this is like knowing the number 1 for matrices. So, and as an example, here's what I'm calling I3. Usually I'll just write I, but I want to emphasize this is for 3 by 3. And that is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, hopefully you agree that if I is not J, you get 0. And if I equals J, you get 1. So 1's in the diagonal, 0 everywhere else. Any questions on this definition? All right, here's an easy question. I hope it's easy for all of you. What is the I sub 1 instead of I sub 3? What's the matrix I sub 1?
1.
Yeah.
Yeah.
But you'd probably put parentheses around it. So that would just be 1. They're kind of boring.
Also, that's a small question I had. Does it matter if we use parentheses or square brackets? Because I've seen both used.
Right. You'll see both used. I typically use parentheses, but you could use either. Here's what you shouldn't use. So I'm glad you brought this up because there's one that you shouldn't use. You shouldn't use vertical line segments. So
That implies absolute value, right?
Nope. No, because absolute values are for numbers. Yeah, so it doesn't apply. It doesn't mean make them all positive. We're going to have a whole section on it. It means determinant. So don't use vertical line segments because that means determinant. But whether you use parentheses or brackets, I don't know. That depends on what mood you are and when you wake up in the morning. So either way, it really doesn't make any difference. I tend to like parentheses, but I don't really care. But don't use vertical line segments because that has a very special meaning. And we'll be using that a lot for determinants. Okay, any other questions about the identity? Do you agree identity is easy? Okay, all right. So theorem, and I'm going to write a little note. For the correct dimensions for multiplication, IA equals AI equals A. Okay, and I think I want to convince you by maybe doing an example. I think it's worth seeing an example. So here's I. Now let's throw in some numbers, make it an A. Just, oh, shoot. Good thing there's a Control Z. I'm just picking some random numbers. And let's see why this has to be true. Okay. Well, what does it mean to take I times A? It means you multiply it, right? So that means we're supposed to take the dot product. So let's look at this first. Let's look at the first row by the first column. And you're going to get the 1 times 3, and then you're zeroing out everything by definition. Do you see that? Because you always have zeros after that first 1. So all you're going to get is this first 3. Do you see that? So let's do these one at a time. And we know what we're going to get. So I'll write equals, and I'll just copy and paste it because it better be true. But let's see why. Oops. Yeah. There's equals. Okay, so again, what I'm going to do is I'm going to take this 301 column, and I'm going to dot it. I'm just going to get the first column. I'm going to dot one at a time. Well, the first time I dot, I'm taking 1 times the first number, and that's going to give you the 3. And then this 301, if I go down 1, I'm going to pick out the second number, which gives you the 0. And then the 301, I'm going to dot times the third row, and that's going to pick out the third number, which gives you the 1, and that's why I get the 301. Are you convinced, or do I have to keep going? Okay, and you could prove this. It's just a bunch of I's and J's. Huh?
I said I think I'm convinced.
Yeah, this can be proved. It's just a lot of I's and J's to talk about. I think seeing an example, it convinces you pretty fast what's going on, if you really can see it. Okay, because by dotting, you're picking out just the number, whatever number you're looking at, first, second, third, depending on which row you're in. And that's what we want. Any questions on this theorem? Okay, what that is, let me just restate the theorem in words. And the words are the identity matrix is the multiplicative identity. Okay, and that way we can actually just talk about multiplicative identity. Multiplicative identity means in multiplication, if you multiply it by something, you get what you started with. So the theorem is a theorem that says the identity is a multiplicative identity, that we've chosen a good word, identity, because it really is. That's what this theorem says. Any questions on the theorem? Okay, it's very important. We're going to use it a lot. And it's easy. Do you agree? Right? So we can think of I as 1, and 1 times A is A. That's all this is. But it's a special one. Just like 0 is a 0 matrix. I is the 1 matrix, but not the matrix of all ones. It's a matrix that works as a 1, like 1 works for numbers. This identity works for matrices as a multiplicative identity. Any questions on that?
I have a quick question.
Mm-hmm.
Would this be like synonymous to a unit vector?
Not quite. Not quite, because it's truly multiplicative identity. So let's go to 3 by 3, a 3-dimensional unit vector, because otherwise you can't even talk about identity for vectors, multiplicative identity. Then you want to say, well, is there a vector such that if you cross it with another vector, you always get what you started with? Does that make sense? And the answer is no. It turns out there is no multiplicative identity for vectors. Does that make sense?
Yeah.
Yeah. So it's not quite, it's definitely different. Very different. All right. So I want to mention, as I'm going to get to the next definition. And this is a definition. This is not, I'm not teaching anything now. I'm going to see if you remember something that you're supposed to know. Okay. And when I say supposed to, means there's a good chance you don't remember. So this definition is not a linear algebra definition. This is a basic math definition that you're supposed to all know, and supposed to does not mean you really do. But you might. Okay. Some of you, the tutors better know, by the way. Okay. And that is f and g are inverse functions if what? Do you remember?
If f of g equals 0.
Not quite. You're good until the end.
If f of g equals just the variable by itself, x.
Yeah.
Yeah.
Yeah, there we go. So let's write it out. So f of g of x equals, and actually you need it in 2 ways. You need g of f of x. You need both to be equal to x. Okay. So again, I didn't expect all of you to be able to say the right definition, but I do expect all of you to look at it and say, oh yeah, I've seen it. Are you good with that? All right. So now, given the fact that matrix multiplication is composition of functions, I don't know, I've said it, I haven't proven that, but it is, because we haven't talked about matrices as functions, but it is. Then this ought to be true. Now, what function is the function x?
It's linear.
It is linear, but so is 3x plus 4. So it's even more special than linear. In one word,
It's identity.
it's the identity. Okay. So now we can move on and talk about what it means, instead of for functions to be inverses of each other, what does it mean for matrices to be inverses? And what we say is now you don't write f of g of x, we just write a times b. So if a times b equals b times a equals the identity, then b is called the inverse of a. And by the way, a is also the inverse of b. Goes back and forth. And we write that b equals a superscript -1. And we read that as b equals a inverse. Okay, and we, oops, not day, we say that a is invertible. By the way, let's go back to the function definition inverses. Is there always a g? Does every f have a g such that f of g of x equals x? Can we always find an inverse of a function?
Not always.
No, in fact, not most of the time. Do you agree? Right? Like sine of x doesn't have an inverse, not over all x's. Okay, I know there's the arc sine, but that only works for a limited range, right? Or limited domain, sorry. Okay, or x squared over all x does not have an inverse. Do you agree? Similarly, not all matrices A and B, or not all matrices A have inverses. Okay. Any questions on that? All right, so that's just a big note, is just because we have this definition of inverse does not mean that every matrix has an inverse. But if it does have an inverse, we say it's invertible. Okay, and that's a really important word, by the way, in this class, invertible. All right, I think I'm going to give you a minute to do this yourself. Let's suppose A is 3, 7, 2, 5, and B is 5, -7, -2, 3. Let's see if you can show A and B are inverses. I want you to do it on a piece of paper, and then tell me if you get stuck, or if tell me you got it and now you understand it. It shouldn't be hard, that's a hint. So a little bit of calculation, nothing too bad. So you should be writing now. And let me know, put in the chat box to say you're done or you need help when you're at either point. And the hint is you're gonna have 4 different dot products to do. But they're easy. All right, we got one done. See if we can get a few more. All right, I'll wait till one more. Okay, so Was it any questions on how to do it? I'm assuming that you can. I don't have to go through it unless you need me to. You just multiply A times B and you should get 1, 0, 0, 1. And then you multiply B times A and you should get 1, 0, 0, 1. Everyone good with that? So it's just a matter of multiplying to check to see if they're inverses. Any questions on that? Okay, no big deal. Okay, by the way, with functions, it's not that hard to check to see if they're inverses, right? But is it easy to find an inverse of a function?
It depends on the function.
Yeah, but in general.
I don't remember it being too hard, but when we were finding them, we didn't really have a lot of different functions to play with. So
Yeah, so if I gave you in general, so for example, if I gave you something like, I don't know, how about 10x plus cosine of x, and I said find the inverse, you wouldn't be able to. Okay, just let you know that. Okay, and the inverse does exist, by the way, but you wouldn't be able to, not because you haven't had as much math as me. I wouldn't be able to either. Okay, I could do it power series, and my guess is you probably couldn't. It would be really hard, but it's doable. Inverses are really hard to find with functions, and with matrices. What do you think? Any guess?
I'm willing to bet it's probably harder.
No, it's not. But it's hard.
easier? Oh, it's okay.
It's hard, and as soon as the matrices become big, it takes too long. It turns out that the amount of computations is of the order of n factorial. And so if you have a 20 by 20 matrice, computer can't do it. Does that make sense? Because 20 factorial is too big for a computer, basically. So matrices just it's busy work to find the inverse of a matrix, but we'll do that in a minute. But I want to warn you. First, I'm going to do the fun stuff and easy stuff. A matrix A is called symmetric if A equals A transpose. And it's called skew symmetric if A equals negative A transpose. So let's take a look. All right, here's a couple matrices. Is the first one symmetric, skew symmetric, or neither? What do y'all think? This 3, 4, 6, 4, 1, 0, 6, 0, 2 matrix. Symmetric, skew symmetric, or neither? It shouldn't take more than a second, by the way, just to let you know.
I think the first one's probably neither.
I just look at the first one. Okay. Any other guesses? The hint is just take the transpose. Just look at it and take the transpose. Do y'all know what it means to take a transpose? You remember we talked about that on Friday?
It's you switch the I and J, right?
Yeah, you switch the I and J, and what that means is that you flip it across the diagonal.
I just don't see a second 3, so I'm wondering.
Okay, so if I take this 3 and I reflect it across the diagonal, well, it hasn't moved. It's on the diagonal. That's A11. Well, is A11?
Oh, okay. So you flip it. Okay. Yeah. Then.
So I switch 1 and 1. If I switch 1 and 1, I still get 1, 1. Do you see that?
So yeah, it's symmetric, but not skew.
Right. This one's symmetric. Right. This is symmetric. And in fact, there's only one matrix that's both symmetric and skew symmetric. And what matrix is that of any square dimension?
3 by 3.
Yeah, but what specific matrix? In one word.
0.
0. 0 is the only one that's both. So you're never going to get both unless it's a 0 matrix. Because if you take the zeros and you flip them and multiply by -1, it doesn't change anything, right? If you flip them, it doesn't change anything because there's nothing to change. But this is symmetric. Do you see that? Okay. Now, how about the second one?
That's skew symmetric.
Yeah, that's skew symmetric because if I flip it and multiply by -1, I get back to what I started with. So if I take this -2, move it over here and multiply by -1, guess what? I get a 2. And you can try that for all of them. And notice that if it's skew symmetric, what do you know about diagonal always?
That it must be 0.
Yeah, it must be 0 because if you flip it, nothing happens. So if I multiply by -1 and I say nothing happened at the end, that means I better have started with a 0. Because if I have any other number and I multiply by -1, I get something different. I get the negative of it. Do you see that? So diagonal must be 0 for skew symmetric matrices. Any questions about this definition? And it comes up here and there, not even close to important as a definition of inverse, by the way. Inverse is the biggie. These are little definitions. So
What was
sometimes I
the
like to
definition of transpose again?
transpose. So Aij transpose, let me write it out. It's easy. That's important because that will come up. So I guess the other way around. A transpose Ij is equal to A Ji. So that's the definition of transpose. So you take the transpose by switching the ijth component, and it means that all rows become columns and all columns become rows. Because remember, I and j is row element, j column element. Any questions on that? And one reason why square matrices are so important is that A transpose is still a square matrix, is you're not changing the dimensions when you take a transpose. Any questions on that? Okay, I'm going to say something that my guess is nobody would have guessed, but when you're doing regression analysis, transpose is really important. Now, today I'm not going to tell you why, that comes later, but it's really important.
Like a linear regression?
Yeah, AA transpose. It's all about AA transpose, not just linear regression, annual regression, quadratic regression, whatever, cubic regression, logarithmic regression, all that, AA transpose. So it comes up a lot. And as I mentioned, artificial intelligence is all about regression analysis, or it's a big piece of it. So just note that. So it's a big, big application. Okay, now I mentioned that finding the inverse could be really tedious and hard, but not impossible if there exists one. Here's the steps. Step-by-step process. Step 1, write out the matrix AI. Okay. So we want to write out the matrix AI, where basically it's side by side. Step 2, you RREF to get IB. Okay, if you RREF and you don't get I there, then it's not invertible. Step 3 is you write down that B is equal to A inverse. So this B that you get on the right-hand side after you've RREF'd will be the inverse of A, as long as you do get the identity on the left-hand side. And those are the steps. Looks easy, doesn't it? What's the hard part?
Probably RREFing it.
Yeah. Imagine RREFing a 20 by 20 matrix by hand.
I really don't want to.
No, you never want to. Even imagine having a computer do it. Okay, it turns out that it's too many steps for a computer even. Okay, but a 3 by 3 or a 2 by 2, we could do that. Okay, do you agree? Okay, a 1 by
Yes.
1, that's really easy. Because the inverse is really the same as the inverse of numbers. What? Any guess on what the inverse of the matrix 5 is? So the 1 by 1 matrix with entry 5. The hint is it's what you would guess.
1.
No, that wouldn't be the inverse for 5.
1/5.
1/5. That's the inverse of the matrix 5. And that's because what is 5 times 1/5?
1.
1. And that's, remember, the dot product when you only have one variable is just multiplying, right? So 1 by 1s are boring. Do you all agree? I know you're hoping I put one on the test, but I'm not going to. But we could do a 3 by 3, and I'm doing a nice easy 3 by 3. So let's see if we can find the inverse of this matrix here. 2, 0, 0, 0, 1, 0, 0, 1, 1. Any questions on that? All right, so what I do is I need to take this matrix and I need to put in the identity to the right of it. Any questions on that? So what I'm going to do is I'm going to insert some more columns. Oh, shoot. After, not before. Column after. There we go. And let's get a couple more. Now, it's a lot easier to do it by hand than it is to do it using Microsoft Word, by the way. Just a warning, just to let you know. You don't have to do this right click and stuff. And what I'm going to put in here is the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. Any questions? That was step 1. Any questions with step 1? Okay, what do we do next?
Put the identity into the matrix.
Yeah, next to the matrix. I mean, I made a new matrix where the left-hand side is the original and the right-hand side is the identity.
Okay.
Okay. So that's what I've done. All right, what's step 2? Step 2.
RREF it.
REF. Okay, so what should I do? That's a lot of steps to RREF. What's the first step?
Multiply the first row by 1/2.
Yeah. Okay. Sorry, I'm drinking a lot of water. Believe it or not, I have 6 hours in a row of Zoom without a break. So water's going to happen. Okay, so I'm going to multiply the first row by 1/2. And I get 1 there. And I get a 1/2 there. Look good so far? Okay, what's the next step?
Let's multiply -1 by row 2, add it to row 3, and store it in row 3.
Yep. Okay. So what I'm going to do is I'm going to do that. And when I do that, this 1 becomes a 0. And then this 0 becomes a -1. Any questions on that? Okay, do we have it RREF'd?
Yes.
Okay, we do have it RREF'd. Now look at the left-hand side, the 3 by 3 on the left. Is that the identity matrix?
No.
One more guess.
Yes.
Yes.
Yes, it is. It's 1 0 0 0 1 0 0 0 1. If you look at the first 3 columns. That's the identity by definition, right? So we've finished step 2. And we've decided that this is invertible. And now we're ready to write down the inverse. So let's write that down. And that is A inverse is equal to and now we just write down the right-hand side. 1/2, 0, 0, 0, 1, 0, and 0, -1, 1. Any questions on that? Any questions? All right, so now here's a 2 by 2 matrix. And I want you to find the inverse if there is one, or if there isn't, explain why there isn't. So I'm going to give you a minute or two. Shouldn't take too long. This is 2 by 2, which is a lot smaller. Do it on paper and pencil. And let me know what the inverse is, or if there isn't, why there isn't. So give it a shot using the step 1, step 2, step 3.
I know why.
Why
It
what?
does not have an inverse.
You're saying it doesn't?
Yes.
Okay. Anyone else agree that it doesn't have an inverse? And if not, tell me what the inverse is. Because that's
I agree.
You agree.
Yeah, I agree as well.
Okay. So if we go ahead and we do it, I think it's worth it to do it. So what I'm going to do is I'm going to put in another column and one more column. And put in the identity. And then I need to RREF. So what do I do to RREF?
Multiply -2 by row 1, add it to row 2 and store it there.
Good. Okay, so that 2 becomes a 0. What does a 6 become?
A 0.
A 0. And this 0 becomes a -2. And the 1 stays the same. Okay, is this RREF'd?
Yes.
Yes, it is RREF'd. Is the left-hand side 2 by 2 matrix the identity?
No.
No. So therefore, since, actually I should say since first, I guess. Since the left-hand side 2 by 2 matrix is not the identity, the inverse does not exist. Any questions on this process? All right, so you really don't know if an inverse exists until you try it. Okay, are we going to have some theorems about inverse existing and not existing?
Hopefully.
Yeah, the most important theorem of this whole class is called TFAE. Have you seen those letters before in a math class? Because it comes up in lots of classes, but have you heard of it? It means the following are equivalent. And one of them is the function, the matrix has an inverse. And then we're going to have a whole lot of other things And if any of those happen, then you know it has an inverse. And if any of those don't work, then it doesn't have an inverse. So we're going to spend literally the next 2 months talking about TFE. And one little piece at a time. Everything we do, we're going to say, and this gives us another TFE item. Right now, all we have is, how do you tell if it has an inverse? Okay, but we're going to have a whole lot of other ways too. Any questions on that? Okay, I'm going to ask you, this is a very easy question. If I gave you, let me insert an equation, y equals 5x. And I said, solve for an x. What would you do? I promise this is easy. If you don't know it, then you don't belong in this class.
X equals y over 5.
Yeah, and how did you do that?
Divided both
Divide by
sides of the
5,
equation
yeah.
by 5.
Right, now I'm going to say it in different words. I'm going to multiply by the multiplicative inverse of the number 5. I know that's a fancy way of saying divide by 5. But I want to say it that way because that's what we're going to be doing. So in particular, we want to solve ax equals b, where a equals 1, -1, 1, 2, and b equals -1, 5. So let me write it this way. It'll take a moment, but it's worth it. So if I have, you know what, I should have just copied it and pasted. That times x, let's call it xy. Equals -1, 5. I think it'll let me do this. Let's see. Then we learned one way of doing it, and that is writing an augmented matrix and solving, right? But another way of doing it is to say, well, I can take this and I can multiply by the inverse on both sides of this matrix. Do you see that? And I can write xy is equal to this matrix 1, -1, 1, 2 inverse times -1, 5. Any questions on that? Okay, and if you know what the inverse is, this is actually pretty easy. Do you agree? Okay, I'm going to tell you a nice way of finding the inverse of a 2 by 2 matrix. And this always works as long as the inverse exists. And that is, you switch the diagonals and multiply the off diagonals by -1. So if you notice up here, there it is. Notice this A and B that we had before. So notice a 3, 5 became a 5, 3 if you just read the diagonal. And notice that the off diagonals, this 2 and the 7, becomes -2 and -7. Okay, now there's going to be a little more. You have to divide by the determinant, and we'll talk about the determinant. But it turns out for this example, the determinant is 1. So I gave an easy one. So I can now realize, because I've taught linear algebra, so I know what the answer is, because I know how to take an inverse the easy way. just got to get it all on one page. There we go. Is now I can replace this inverse piece by doing that switch the diagonal stuff. It's harder to type than to write. Okay, so the 1 becomes a 2, the 2 becomes a 1. And then this 1 becomes a -1. This -1 becomes a 1. Now that is equal to, well, now we just do matrix multiplication. Okay, so it works just like you do in algebra. To find the inverse is a little messy, whereas in algebra, dividing by a number is pretty easy. But here you got to find the inverse. So then we go ahead and we multiply. So let's do it this way. So what I do is I take the dot product of 2, 1 and -1, 5, and I get 3. You good with that? And I take the dot product of -1, 1 and -1, 5, and we get 6. And there's my answer. So it's a very different way of solving a system of equations. Do you agree? But this always works as long as you have an inverse. If you don't have an inverse, you can't do it. Any questions on this process?
Yeah, I have a question.
Mm-hmm.
So if you want to do the trick you just showed us with the 2x2 matrix,
Mm-hmm.
how do you check to see if you know for sure it has an inverse before you just go and do it?
It's a determinant,
Okay.
which we haven't defined yet. Now, you know it from last quarter. I have to pretend that you don't know what a determinant is. So you actually have to divide by the determinant. So, but in this case, I made it so the determinant, oh, did this work? Oh, it didn't. I made a mistake. Sorry. 2, 3, it should be 1/3 of that. Sorry. Thanks. Much better. That's right. That's right. And then you get nice numbers when you're done. So that, by the way, is equal to 1, 2. Whoa, what just happened? There we go. Any questions on that? So yeah, I lost the determinant part. Now, with a 3x3, it's much harder. Okay, is there kind of a formula like this? Yes, but it's much harder. And with a 10x10, you write it, there is a formula, and what you do is you write a computer program to do it. You would never do a 10x10 by hand, because I don't think you could finish in a week. Okay, but I could write a program in a couple hours and then have a computer finish in 30 seconds for a 10x10. So that's how I would do it. And, you know, since you guys are going to be professionals in some kind of STEM thing, that's how you would do it also. Any questions on this idea? The 1/3, the determinant was 3. So you do determinant if you, again, I'll teach this. We'll have a whole section of determinant. Right now, I'm just saying, trust me. So 2 times 1 minus 1 times -1 is 3. And that comes in that way. Any questions on that? All right, now comes properties. And these are properties of the transpose and the inverse. Some just by itself, some in combination. The first one, my guess is you can all convince yourself that the first one has to be true. A transpose transpose is A. Because remember, A transpose, you reflect across the diagonal. Well, if you reflect twice, what happens?
You went back where you started.
Then that's all this says. So I start with A, I reflect again, and guess what? I'm back at A. Is that clear? Okay, number two. Number two says the transpose can be brought into each matrix if there is scalar multiplication and addition. Okay, and subtraction too, by the way. So CA plus KB transpose is CA transpose plus KB transpose. Any questions on that? All right, number three should be obvious also. A inverse inverse is A. How do you prove that one? It's actually a really easy proof. How do you tell if two matrices are inverses? If I want to find the inverse of A inverse, and I tell you it's B, then that means if I multiply by B, what am I supposed to get?
A.
No. What's the
Well,
definition of inverse?
it's ones, right? Like a matrix of ones.
Yeah, except we don't use one. What do we use?
I.
I. So it's not the matrix of ones, it's the identity matrix, where one is along the diagonal, zero is everywhere else. Does that make sense?
Yes.
The matrix of all ones is unimportant. Just let you know that. There's no name for it because nobody cares. It's not useful for anything that I've ever seen in my life. But the identity matrix is everywhere. Well, if I take this A inverse, and I want to find its inverse, and I say, hey, it might be A, well, let's multiply. What's A inverse times A? It's the identity, right? By definition. And if I go backwards, I get the identity. That's the proof. It's done. The next one's not as obvious, and the proof is a lot harder, but it's nice. And that says that A inverse transpose is A transpose inverse. Okay, and of course, this assumes the inverse exists and all that. But so it's nice. It says that you can switch the order of inverse and transpose. Any questions on that? Okay, the next one also is not obvious, but it's also important. And that one is not something you would expect. If you take A times B and you take its transpose, you do not get A transpose times B transpose. You get B transpose times A transpose. Okay. And the reason why you can't, there's just no way it could just be A transpose times B transpose, is that A transpose times B transpose for a non-square matrix wouldn't even exist. Doesn't even work. You get all kinds of problems. So you won't be able to multiply. And the inverse works the same way. AB inverse is not A inverse B inverse, it's B inverse A inverse. So when you're talking about the inverse multiplication, the inverse of a multiplied two matrices, you can't just distribute the -1 through. You have to switch the order. Okay, and then it works. Any questions on that?
Would the book show the proof of these?
Yeah, basically you prove it using dot products, and they do it with a summation. They do the definition of the dot product with summation. I think it's easier to do dot products, but they do the summation. Yeah, I don't have time to prove everything. Hopefully you understand, but it's important you know all these properties, and especially number 6. Okay, number 7 is important too. If B is equal to A inverse and C is equal to A inverse, then B equals C. In one word, what's the word that talks about that we talked about the very first thing I went over? And it wasn't on my
Unique.
agenda. Yeah, unique. Yeah, this says the inverse is unique. Okay, that if I find my inverse and then you find your inverse of the same matrix, we're going to find the same matrix. Our answer is going to be the same. You're not going to get two different different matrices that work as inverses. Does that make sense? Okay. And one way of proving it, except that it's too advanced because we haven't defined it quite this way, is that, remember I told you matrices are functions? Do you guys remember that? Now, is an inverse unique for functions?
Yes.
Yes, that's a proof right there. But that's pushing the fact that I haven't proven that a matrix multiplication is function composition, or that matrices are functions at all. But maybe I'll mention that. Why are matrices functions? What are they functions of?
I'm going to go out on a limb here and say vectors.
Yeah, they're functions of vectors. Because, let me scroll up a bit. This is why I did this one. Notice we could have 1, 1, negative 1, 2, and multiply by xy. Do you see? So given a matrix, apply it to a vector, and guess what? You get a vector. Okay, and if it's a square matrix, you get a vector in the same universe, right? If it's not square, you don't get the same universe, but you still get a vector. So then you have a domain and range being different dimensional vectors, which is okay. So a matrix is a function of vectors. Okay, and just for fun, I'll tell you a really cool application. I don't know if any of you gamers, computer gamers?
Yeah.
Okay. All right. So when you play computer games, okay, especially nowadays, it's all animated, right?
Yes.
Things move around, right?
Yeah.
How does that happen on the computer? In one word?
Matrices?
Uh-huh. Matrices. So the way you fully code a computer program is you apply a matrix depending on what you want to do to the scenery. And that includes foreground, background, 3D, all of it. And because remember that a pixel is a vector. Do you all know that? Okay. In fact, do you know what the dimension of a pixel is? Dimension of that vector.
Is it 3 for its color values?
Okay. Actually, it's 4 for the color values.
Okay.
But then there's 2 more, because the 2 more is what I expected you to know. And that is your X and Y coordinate on the screen, right?
Oh, yeah.
But then you have the 4-dimensional color values, RGB alpha. Alpha meaning the how visible it is, right? See-through or not see-through, basically. How transparent.
So it's like the saturation.
Yeah, how transparent or how saturated. So now we're talking about a 6-dimensional vector. Yeah, opacity. So we're talking about a 6-dimensional vector, and applying a matrix to a 6-dimensional vector will transform that vector into a new vector. And if you want to do things like rotate it or move it left or right or make it bigger or smaller, zoom in, zoom out, those are all matrices. Okay, so very, very important application. And later on, I'll get to show you, I wrote a computer program that shows you that you do the matrix and it shows you what happens. Okay, not as beautiful as your gaming. Sorry about that. I'm not an artist, I'm a mathematician. But basically a really good computer gaming company is going to hire both. Going to hire artists and mathematician computer programmers. And they're going to get together and do beautiful stuff. Does that make sense? So it's kind of cool. It's a really important application. So inverses do things. I'll let you know that. Okay, and you want uniqueness. If you don't have uniqueness, you got all kinds of problems. So that's a main application, the kind of a modern application of matrices. And the reason I wanted to mention this is I want you to get out of the thought that a matrix is just a system of equations, because that's not what this is doing. Do you see that? So when you're talking about this computer gaming thing, it's not about systems of equations anymore. It's about transformations of the screen. Okay. And you can go further than that, and you can talk about 3D instead of 2D, because good games are in 3D now, right? Okay. And by the way, there's another D also, 4D. What's the other D? So it's 4D plus another 4D, so it's actually 8D. So we got the 3D with the XYZ, you got the 4-dimensional color scheming. What's the other one that's really important in gaming?
Time.
Time. Yep. And that's the other one. And with all of those, you can make a beautiful game. Okay. And you got to have creativity too. There's that piece. You have to have cool ideas. But if you want it to make it look good on the screen, you need to have these matrices. Okay. And computers don't complain about, you know, an 8x8 matrix. We would. I wouldn't want to do an 8x8 matrix and RREF it or do anything with it. But computers don't care. Any questions on that nice little application? Okay, and I'll show you how some of that works later. All right, so these are easy to show. What do you want to see proof? Pick a number from 1 to 7.
Four.
Okay, 4 it is. Okay, number 1, by the way, I could do in about a second, but let's do number 4. It takes me longer because I got to type it with number 1, that stupid computer thing. Okay, so we want A inverse transpose. We want to show that's A transpose inverse. Got it? So that means if I want to show that A inverse transpose is A transpose inverse, that means if I multiply A inverse transpose by A transpose, I should get the identity. You following that? Because that's what it means to be the inverse of a matrix, means that if you multiply by that matrix, you're supposed to get the identity. Do you see that? So that says A inverse transpose is the inverse of A transpose, which means we need to look at, and maybe I'll do one side of 4 because they're both kind of similar. So we need to take A inverse transpose, multiply it by A transpose, and hopefully get the identity. So let's write that out. I need in parentheses A inverse transpose, and then I need to multiply that by A transpose. Okay, any questions on that so far? All right, now I want to see, do I get the identity or not? Well, we got to think about what does this mean to say A inverse transpose? Well, what does a transpose do? In words instead of symbols is better.
Changes the orientation of the matrix.
Yeah, it changes the orientation. In particular, rows become columns and columns become rows. Got it? Okay, any questions on that? Okay, but even better, and I don't know if it's cheating or not. Let's see, I'm on number 4. Yeah, it's kind of cheating because if you use number 5, it's immediate. Because what does 5 say? I think I'm going to prove it with 5 because it's so easy. What does number 5 say? It says that if I read 5 backwards and I take B transpose A transpose, I get AB transpose. So I can rewrite this as A times A inverse all transposed. Right? That's using number 5. Now it turns out it's easier to do that and then prove number 5. because 5 is not hard to prove. Okay. Well, what is A times A inverse?
The identity.
Yep. So that's the identity transpose. But what is the transpose of the identity?
The identity.
It's the identity because the identity is symmetric, right? Right. If you look at the off diagonal of the identity, it's all zeros, right? Well, if I switch those zeros from top to bottom, guess what? If I change this 0 to this 0, well, I still have the zeros. Do you see that? So it's just the identity, and that's done. Okay, but of course I use number 5, so I guess I should prove number 5 to show that my proof of number 4 was correct. Do you see that? And that's AB transpose is B transpose A transpose, but that's actually not that hard, because what is AB? Since we only have a few minutes, I don't know if I'll type it all out, but I'll say it at least. What's the definition of multiplying matrices?
The dot product of those two matrices.
Yeah. So for number 5, whoops, let's do 5. There we go. For number 5, how about that way? Good. Notice that AB is the dot product of the ith row with the jth column. Okay, and that's the ijth component. I'll just write ij. Is that clear? But we want the transpose of that. So we don't want the ijth component. We want the jith component because we're switching, right? So ABJI transpose is a dot product of the ith row with the jth column, because that's what transpose means, switch I and J. Any questions on that? But what is B transpose times A transpose? Well, when you're multiplying, that means you're going to take the ith row of B transpose with the jth row of A transpose. But rows become columns when you do a transpose. And then it works. So we're going to take the jth row. So we're going to take the jth row of B with the ith column of A, because you got to switch I and J, and then it works. So this is the same as B transpose times A transpose. I'll just write AT and BT for transpose because I don't have time to type it all out. So you have to think about these switchings. Transpose switches columns and rows. And the nice thing is with vector products, it's commutative, right? VW is WV. So I can think of it that way. And that's the proof of number 4 using number 5. And now I proved number 5, so it must be true. So let me unshare. Just somewhere around here. And I think I'm going to stop the recording. So thanks a lot. Hopefully this makes sense. I didn't lose you too much.